Every time we train an AI model, it learns from data, lots of it. But that data usually lives in different places, on phones, hospital systems, enterprise servers, or private cloud environments. Now, what happens when you can't move that data because it's private or sensitive? Do you stop training the model? Or find new ways to learn without ever seeing the data itself? That's where federated learning comes in. It's a way for AI to learn from distributed data without ever transferring that data to a central location. Picture this. You've got 3 clients. Each holding sensitive data sets that they can't share. So instead of sending all that data to one big server, each client trains its own local model on-site. Then only the learned updates, the gradient information, not the raw data, are sent to central coordinator. That coordinator performs secure aggregation, combining the encrypted gradients from each node to improve the global model, and then sends that model back to every participant. No personal records ever leave the original environment. The data stays local, but the intelligence is shared. That's federated learning in one line. Train locally, learn globally. This approach solves one of the hardest challenges in AI today: how to train models on sensitive and regulated data while maintaining privacy and compliance. It allows developers and data scientists to collaborate across distributed environments, all without exposing any kind of private information. Federated learning has become a core pillar for trustworthy and explainable AI, systems that can be audited, secured, and scaled responsibly. But here's the next challenge. Even if data never moves, how do we make sure that updates we share aren't revealing anything sensitive? That is handled by encrypted AI agents. They use advanced cryptographic techniques like homomorphic encryption and secure multi-party computation, so models can learn from encrypted gradient updates, literally data that they can't see. Think about that for a second. The agent is blind to the actual data, but can still compute over it. It's like grading a test while all the answers are hidden, and still getting the right score. That's the magic of encryption in AI. And it's how we ensure secure data aggregation while maintaining model performance. When you combine federated learning with encrypted agents, you get the best of both worlds: privacy from keeping data local, and security from computing on encrypted information. Together, they form what's often called privacy-preserving AI architecture. Each node, whether it's an enterprise server, an IoT device, or a smartphone, becomes an intelligent agent that trains locally, encrypts its gradients, and then contributes safely to shared global model using secure aggregation protocols. We can take another real-world example. Let's say several research labs are training a model to detect early signs of heart disease. Each lab trains its own convolutional network on-site with local patient data. After training, the encrypted gradient updates are securely transmitted to the aggregator. The aggregator applies homomorphic addition over these encrypted updates, producing a smarter global model, without a single record or raw feature leaving any lab. That's collaboration without compromise. In the past, privacy meant sacrificing model performance or scalability. Now, with federated learning and encrypted AI agents, privacy and performance can finally coexist. We can build distributed systems that are both data respecting and high performing, ensuring that the model training remains secure, auditable, and compliant even across global networks. That's a big step towards ethical, decentralized AI that the world can actually trust. AI doesn't have to choose between intelligence and privacy. Federated learning and encrypted agents are showing us how to achieve both, learning from everywhere while keeping data where it belongs. Because real innovation doesn't just build smarter systems, it builds trust into every layer of intelligence.